In this video, we're going to work through an improper integral example. And the reason we know that it's an improper integral, we're doing an integral because we want to find the area under the curve, but the bounds of integration, our interval, is not finite. It's not closed. It goes to infinity. Now, I already pulled this picture up on the screen in the first video, but I'm going to pull it up again so we know the space of the region at which we're looking. So here's our picture. This is the graph of the curve, and we are looking at the area under the curve from 1 to infinity. And obviously this is approaching 0, but it is never becoming 0 because we have a horizontal asymptote here. So in the previous video, we talked about improper integrals of type 3, and we said there were 3 different cases. This is case 1, from a finite value a to positive infinity. So the way we're going to set this up is I'm going to say that the area under my curve equals the integral from 1 to infinity of the function. My integrand is ln x over x squared, and then again integrated with respect to dx. So I'm not allowed to have this infinite number in here. So we take this infinite number and we rewrite it, and I'm going to say, well, this is the same as doing the limit, and that would normally be my b value. So the limit is b approaches positive infinity of the integral from 1, I'm replacing that infinity with b, ln x over x squared dx. Now this is going to be integration by parts. We're going to integrate this from 1 to b, and once we have that value, then we're going to find the limit as b becomes closer to positive infinity. So integrating this with integration by parts, I use Liate to help me determine how to choose. And of course, because I have a logarithm in the numerator, which comes before algebraic, which is what I have in the denominator, I'm going to let u equal ln x, and then v prime is 1 over x squared, or x to the negative 2. So the derivative u prime of ln x is 1 over x, and the integral of v is negative x to the negative 1. So this is equal to the limit as b approaches infinity. We're going to put a brace here. So this is going to be uv minus the integral of vu prime. And just for the sake of making my life easier, I'm going to rewrite this v as negative 1 over x. So uv, I end up with ln x over x, and we have a negative in the front. We need to evaluate that from b to 1 minus the integral from 1 to b of vu prime, which is negative 1 over x, times 1 over x dx. So I'm going to give myself a little more space. I've got the limit as b approaches infinity of, I've got negative natural log of b over b minus negative natural log of 1 over 1 minus the integral from 1 to b. And simplifying this, this is negative 1 over x squared, or in a sense, negative x to the negative 2. And if I pull that negative in front, that's going to be plus x to the negative 2 dx. So looking at this term, the natural log of 1 is 0. This term's going to disappear. This is easy to integrate. So I've got the limit as b approaches infinity of negative natural log of b over b. That would be plus 0. This is 0, so we don't need to write that. plus integrating this using my power rule, I'm just going to get negative x to the negative 1. And that needs to be evaluated from b to 1. So this is the limit as b approaches infinity of negative natural log of b over b minus, I have b to the negative 1 minus b, oh, sorry, that would be 1 to the negative 1. So I just went ahead and pulled that negative out in front, b to the negative 1, 1 to the negative 1. So now we have to look at simplifying and then calculating our limit. I've got the limit as b goes to infinity of negative natural log of b over b minus 1 over b, and then minus a negative, that becomes 1 over 1, which is plus 1. At this point, we've found the value of our integral, and we need to evaluate this limit as b approaches positive infinity. So 1 over infinity is going to go to 0. And then this first one will go to 0 by L'Hopital's rule. So this is 0 by L'Hopital's. This goes to 0. And I end up with the limit as b approaches infinity being 0 plus 1, which is just 1, which lets me know that the value under the curve of natural log x divided by x squared from 1 to infinity converges and has a finite value for its area of 1. So that's how we solve an improper integral of type 1 with an infinite limit of integration and infinity in our integration bounds. And that was case 1 of those 3 cases for type 1.